Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a circle that is inscribed by this triangle ABC. Or triangle ABC blocks this circle. In addition, you know that side AC of triangle ABC equals to 7 units in its left, side AB equals to 6 units in its left, side BC equals to 9 units in its left. Again, our task is to find out the area of this green shape. So first of all, we define this angle ACB is theta. Angle ACB equals to 30 degrees in its side. So here we can implement the law of cosines. Okay, click on the law of cosines. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. Side AB equals to A units in its left, side AC equals to B units in its left, side BC equals to C units in its left. Angle BAC equals to theta. So this triangle ABC that could be any triangle. Cosine theta equals to A square plus B square or C square over 2 times A times B. Again, cosine theta equals to A square plus B square or C square over 2 times A times B. You can implement all the law of cosines in our drawing. According to the law of cosines, in our drawing we get that cosine theta cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. It again, according to the law of cosines, if we implement the law of cosines in this triangle ABC, we get that cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. So 7 square is 49, plus 9 square is 81, minus 6 square is 36, divided by 9 times 7 is 63, 63 times 2 is 126. So then if you found out that cosine theta equals to 49 plus 81, that is 140 minus 36 over 126. 140 minus 36 is 96 over 126. So cosine theta equals to 96 over 126. 96 over 126 is 0.7169. So in total we found out that cosine theta equals to 0.7169. And again, cosine theta equals to 0.7169. We would like to find out the value of theta itself, the size of angle theta. In order to find out the size of angle theta, we'll operate the opposite fraction of cosine, that is arc cosine, on the result of cosine theta. On the result of cosine theta is actually 0.7169, and in this way we get the value of angle theta itself. So the opposite function of cosine is arc cosine. We'll operate the opposite function arc cosine on the result of cosine theta, that is 0.7169. In this way we get the value of angle theta itself. So we should find out that arc cosine 0.7169 is equal to the size of angle theta. and our cosine of 0.7169 is equal to 40 degrees, 40.368 degrees. Okay, again, theta equals to 40.368 degrees in its size, and therefore 180 degrees minus theta will be equal to 180 degrees minus 40.368 degrees. It is actually equal to 139.362 degrees. Okay, again, in total we found out that 180 degrees minus theta is equal to 139.362 degrees. In the next step, we find out the semi-perimeter of this triangle ABC. The semi-perimeter of any triangle is equal to the perimeter over 2. That is to say, it will be equal to the sum of the three lengths of triangle ABC, that is actually 6 plus 7 plus 9 divided by 2. So, the semi-perimeter of triangle ABC is equal to the perimeter over 2. That is to say, it will be equal, so the semi-perimeter, we define the semi-perimeter as S. So S equals to the perimeter over 2. The perimeter is the sum of the side lengths of triangle ABC. That is actually 6 plus 7 plus 9 divided by 2. 6 plus 7 is 13, and 13 plus 9 is 22, divided by 2. The semi-perimeter equals to 22 over 2, that is 11. So the semi-perimeter of triangle ABC is equal to 11 units in its length. In the next step, we find out the area of this triangle ABC according to the formula that says that the area of any triangle is equal to the square root of S times S minus A times S minus B times S minus C. And again, the area of any triangle equals to the square root of S times S minus A times S minus B times S minus B. A, B, and C are the lengths of the triangle, and S is the semi-perimeter of the triangle. We already found out that the semi-perimeter of triangle ABC is 11, so the area of triangle ABC will be equal to the square root of S is 11 times S minus A. A is 6. That's one side of this triangle ABC. It is 6. So S minus A is 11 minus 6. That is 5 times S minus B. S is 11. B is 7. So 11 minus 7 is 4 times S minus C. S is 11 and C is 9. So it is 11 minus 9, that is 2. So in total we found out that the area of triangle ABC equals to the square root of 11 times 5 times 4 times 2. Here we'll take out 4 of this out of this root and get that the area of triangle ABC in total will be equal to the square root of 4 is 2. So inside the root we left only with 11 times 5 times 2. So it is 2 times the square root of 11 times 5 is 55, and 55 times 2 is 110. So in total we found out that the octagon ABC is equal to 2 times the square root of 110 square units in its size. 2 times the square root of 110 units. It's the size of triangle ABC is equal to 2 times the square root of 110. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent AB with this circle. This point is point P. Likewise, we define the point of tendency of tangent BC with this circle. This point is point Q. And finally, we define the point of tendency of tangent AC in this circle. This point is point S. In the next step, we join points O and Q together by a straight line. Point O is the center of the circle. Point Q is the point of the circle itself. Actually, point Q is the point of tendency of tangent BC with this circle. So point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle that we define as R. So here you can implement all one. And for the following to all one, we have the radius OQ that is equal to R. The radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and S together by a straight line. OS is of course the radius of the circle that is equal to R. Again, we can implement the rule 1. According to rule 1, this angle equals to 90 degrees. This angle also equals to 90 degrees. We can implement in our drawing also rule 2. So repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. In the drawing, we have a circle. Point P is the common start point in relation to the circle. From the common start point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. You can definitely implement rule 2 in our drawing. Well, put in our drawing, if we focus on this common start point, point B, from the common start point, point B, we have two tangents to this circle, tangent BQ and tangent BP. And according to rule 2, they are equal to each other. That is to say, BQ is equal to BP. So if you define the length of PQSA, then the length of BP, tangent PP must be also equal to A unit in its length because they are equal to each other. AB in total equals to 6. Therefore, AP will be equal to 6 minus A. Again, AP will be equal to 6 minus A. Again, AB in total equals to 6. BP equals to A. And therefore, AP will be equal to 6 minus A. Again, AB that is 6 minus AP that is A equals to AP that is 6 minus A. We will implement also on the common standpoint point A. From the common standpoint point A, we have two tangents to this angle, tangent AP and tangent AS. And according to all two, they are equal to each other. That is to say, AP equals to AS. So we define the AP, but AP equals to 6 minus A, therefore AS must be also equal to 6 minus A units in its length. Here we BQC equals to BC minus BQ. Again, BC minus BQ equals to QC. So BC equals to 9, BQ equals to A, and therefore QC must be equal to 9 minus A. Again, BC equals to 9, BQ equals to A, and therefore QC must be equal to 9 minus A units in its length. Here we will implement all two on the common standpoint point C. From the common standpoint point C, we have two tangents to this circle, tangent CQ and tangent CS. And according to all two, they are equal to each other. That is to say, CQ equals to CS. But CQ equals to 9 minus A, and therefore CS must be also equal to 9 minus A units in its length. We know that AC equals to 7 units in its length. Again, AC equals to 7 units in its length. So AC equals to AS plus SC. Again, AC equals to AS plus SC. AC equals to AS plus SC. AC equals to AS is 6 minus A, plus SC is 9 minus A. So in total we found out that AC equals to 6 minus A plus 9 minus A. Yeah, AC equals to 6 minus A plus 9 minus A. AC is 7. AC is one side of the big triangle ABC. Is equals to 7 units in its length. So AC equals to 7, and 7 equals to 6 minus A plus 9 minus A. 6 plus 9 is 15, minus A is minus 2A. So if you found out that 7 equals to 15 minus 2A. Here we will add 2A to this equation, and then we subtract 7 simultaneously, and we get that 2A equals to 15 minus 7 is 8. 2A equals to 8, here we will divide this equation by 2, and finally get that A equals to 8 over 2, that is 4. A equals to 4 units in its length. This is 8, this equals to 4. Here also A equals to 4. 6 minus A is 6 minus 4, that is 2. Here 6 minus A is 2. 9 minus A is 9 minus 4, that is 5. Yeah. 9 minus A is 5. So, in the drawing, we have this is quadrangle QASC. This is quadrilateral QASC. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. So which angles we have inside quadrilateral OQCS? We have here, this is a right angle. Let's go to 90 degrees. This is also a right angle, equal to 90 degrees. This is angle theta. This is the missing angle QOS. So the sum of those four angles inside quadrilateral OQCS must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, in quadrilateral OQCS we have four angles as follows: 90 degrees plus 90 degrees plus angle theta plus the missing angle QS must be equal to 360 degrees according to the rule that I mentioned. 90 degrees plus 90 degrees is 180 degrees, so it's 180 degrees plus theta plus the missing angle QOS must be equal to 360 degrees. So as you know, 180 degrees plus theta plus the missing angle QOS, total must be equal to 360 degrees. Here we subtract 180 degrees from this equation, and we get that theta plus the missing angle QOS is equal to 360 degrees minus 180 degrees is 180 degrees. So in total we found out that theta plus the missing angle QOS is equal to 180 degrees. Here we subtract angle theta from this equation and finally get that the missing angle QOS is equal to 180 degrees minus theta. So actually this is the missing angle QOS is equal to 180 degrees minus theta in its size. But we already found out that 180 degrees minus theta equals to 139.632 degrees. So this angle is equal to 180 degrees minus theta is equal to 139.632 degrees in its size. We have the equation that says that the area of any triangle that blocks a circle is equal to the semi-perimeter of the triangle that is S times the radius of the circle that triangle ABC blocks. And again, the area of triangle ABC that blocks a circle is equal to the semi-perimeter of the triangle times the radius of the circle that triangle ABC blocks. We already found out that the semi-perimeter of triangle ABC equals to 11 units in its length. And we already found out that the area of triangle ABC is equal to 2 times the square root of 110 units. It's 2 times the square root of 110 units times the radius of the circle that triangle ABC blocks. Let's say that triangle ABC blocks this circle. The semi-perimeter of this triangle ABC is 11, and therefore, when we put the equation, we get that the area of this triangle ABC will be equal to the semi-perimeter of triangle ABC times the radius of this circle the triangle ABC blocks. So in total, if you found out that the area of triangle ABC is 2 times the square root of 110, and it is equals to S, that is 11, times R. Here we'll divide this equation by 11 and get that the radius of the circle that is inscribed by triangle ABC will be equal to 2 times square root of 110 over 11. And again, I should found out that the radius of this circle that is inscribed by triangle ABC is equal to 2 times square root of 110 over 11 units in its length. Actually, this expression R, or 2 times square root of 110 over 11 is equal to 1.907. So if you found out that the radius of the circle that is inscribed by triangle ABC is equal to 1.907 units in its length. So again, the radius of this circle that is described by triangle ABC, the radius R equals to 1.907 units in its length. In the next step, we'll join points O and C together by a straight line. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape it is equal to the area of quadrilateral OSCQ minus the area of this sector OSQ. Again, the area of this green shape it is equal to the area of this quadrilateral OSCQ, quadrilateral QOSC minus the area of this sector QOS. So I have to know. We actually found out that the area of the green shape, that is the area that we are looking for this question, is equal to the area of quadrilateral OSCQ minus the area of this sector OSQ. Again, if you don't know that the area that we are looking for in this question, that is the area of this green shape, total is equal to the area of quadrilateral OSCQ, quadrilateral OSCQ minus the area of sector OSQ. The rounded line above OSQ, it is the sign for a sector. So what is the area of sector OSCQ. On the drawing, it is very easy to say that sector OSCQ consists of those two triangles. And therefore, the area of sector OSCQ must be equal to the sum of the areas of the two triangles that it consists of. That is to say, it must be equal to the area of this triangle OSC, the right triangle OSC, plus the area of triangle OQC. And again, the area of sector OSCQ must be equal to the sum of the areas of the two shapes that it consists of. For the other, OSCQ consists of two shapes that are two right triangles, and therefore the area for the other OSCQ must be equal to the area of the first shape, that is the right triangle OSC, plus the area of the second shape that it consists of, that is actually triangle OQC, minus the area of this sector OSC. The area of any sector equal to the area of the circle that contains the sector, that is to say pi r squared, times the angle between the legs of the circle, that is 139.632 degrees, over 360 degrees. And again, the area of this sector OSQ is equal to the area of the circle that contains the circle, that is actually pi r squared, times the angle between the legs of the circle, that is 139.632 degrees, over 360 degrees. What is the area of this triangle OSC? The area of this triangle equals to the base of the triangle times the height over 2. The base is OS, we choose the base as OS, times the height is SC, divided by 2. And again, the area of the right triangle OSC is equal to the base OS times the height SC over 2, plus the area of this right triangle OQC. The area of the right triangle OQC equals to the base OQ times the height QC over 2. And again, the area of the triangle OQC equals to the base OQ times the height QC over 2, minus the area of sector OSQ. We already found out that the radius of this circle is equal to 1.907. The radius of this circle is equal to 1.907 units in its length. So we have the area of sector OS equals to pi times r squared. R is 1.907, therefore r squared is 1.907 squared, times the angle between the legs of the sector, that is 139.632 over 360 degrees. So in total, the value of this expression is equal to the area of the green shape. The area of triangle OS equals to OS OS is the radius of the circle, that is R, times SC. We only found out that SC equals to 5 units in its length, so it is 5R over 2 plus the area of this right triangle OQC. This equals to OQ. OQ is the radius of the circle, that is R, times QC. QC also equals to 5 units in its length, over 2 minus the area of sector OSQ. The area of sector OSQ equals to pi times 1.907 square times 139.62 degrees or 360 degrees. Actually, in total, the value of this expression is equal to 4.387 square meters in its size. So, this sector OSQ is equal to 4.387 degrees in its, square meters in its size. So, in total, we should find out that the area of the green shape equals to 5 r over 2 plus 5 r over 2 minus the area of sector OSQ is equals to 4.387 square meters in its size. 5 r over 2 plus 5 r over 2 is 5r. Minus the of sector OSQ that equals to 4.387 square meters in its size. R is 1.907, therefore 5R will be equal to 5 times 1.907, that equals to 9.535 minus 4.367. 9.535 minus 4.367, in total it is equal to 5.148 square meters in size. So if you want to know that they are of this green shape that they are looking for this question is equal to 5.148 square units in its size. That is the answer to the question. I repeat again. If you found out that they have this green shape, in total it is equal to 5.148 square units in its size. So in the next step, I'll summarize the lecture. Our task in this lecture is to find out the area of this green shape. So in the drawing we have a circle that is described by this triangle ABC. We know that side AC of triangle ABC equals to 7 units in its length, side AB equals to 6 units in its length, and side AC equals to 9 units in its length. Our task is to find out the area of this green shape. So first of all, we define angle ACB as theta and implemented the law of cosines in our drawing. So the law of cosines is formed in any triangle. This is a triangle ABC that could be any triangle. This triangle ABC, AB equals to A units in its length, AC equals to B units in its length, BC equals to C units in its length. This is angle BAC, is equal to theta degrees inside. According to the law of cosines, the following equation is told that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Actually implemented the law of cosines in our drawing. According to the law of cosines, we get that cosine theta will be equal to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. And again, according to the law of cosines, this ABC, you get that cosine theta equals to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. 7 squared is 49, plus 8 squared is 81, minus 6 squared is 36, 7 times 9 is 33, and 7 times 9 is 63, and 63 times 2 is 126. So total we have found out that cosine theta equals to 49 plus 81 is 130 minus 36 over 126. 130 minus 36 is 96 divided by 124. So in total cosine theta equals to 96 over 126. And 96 over 126 is 0.7169. So in total if you found out that cosine theta equals to 0.169. We would like to find out the value of theta itself. In order to find out the value of angle theta itself, we'll operate the opposite function of cosine, that is r cosine, on the result of cosine theta, that is 0.7169. This way we get the value of angle theta itself. So r cosine of 0.7169 is equal to theta. And r cosine of 0.7169 is equal to 40.36 degrees inside. So theta equals to 40.368 degrees, and therefore 100 degrees minus theta is equal to 100 degrees minus 40.6. Again, 100 degrees minus theta equals to 100 degrees minus 40.368 degrees is actually 139.632 degrees. So total if you found out that 180 degrees minus theta equals to 139.632 degrees. In the next step, we found out the perimeter, the semi-perimeter of the triangle ABC. The semi-perimeter is the perimeter over 2. And the perimeter is the sum of the lengths of the three sides of triangle ABC. That is to say, it is equal to 6 plus 7 plus 9. And if we want to find out the perimeter, we have to divide it by 2. And again, the semi-perimeter of any triangle equals to the perimeter, that is 6 plus 7 plus 9 over 2. 6 plus 7 is 13, and 13 plus 9 is 22 over 2. 22 over 2 is 11. So the semi-perimeter of triangle ABC equals to 11 units in its length. We have a special formula for the area of any triangle. The area of any triangle equals to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of the triangle. In this case it is 11. A, B and C are the side lengths of the length of the sides of triangle ABC, that are 6, 7 and 9. Therefore the triangle ABC must be equal to the square root of S is 11, S minus A is 11 minus 6, that is 5. 6 is the length of one side of triangle ABC, times S minus B. S is 11, B is 7, so 11 minus 7 is 4 times S minus C. S is 11, C is 9, so 11 minus 9 is 2. So in total, if you know that the area of triangle ABC equals to the square root of 11 times 5 times 4 times 4 times 2. The square root of 4 is 2, so we took out 4 for this root, and actually found out that the area of triangle ABC equals to 2 times the square root of 11 times 5 times 2. 11 times 5 is 55, 55 times 2 is 110. So in total, we found out that the area of this triangle ABC is equal to 2 times square root of 110 square units in size. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent AB. With this circle, this point is point P. We define the point of tendency of tangent PQ with this circle. We define the point of tendency of tangent BC with this circle. This point is point Q. And finally, we define the point of tendency of tangent AC with this circle. This point is point S. In the next step, we join points O and Q together by a straight line. Again, point Q is the point of tendency of tangent BC with this circle. Point O is the center of the circle. Point Q is the point of the circle itself. OQ is the radius of the circle that we define as R. Here we can implement rule 1. We have the radius OQ that equals to 1. The radius OQ is drawn to point Q, that is the point of tendency of tangent BC. If this circle and whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle cosine 90 degrees and this angle also cosine 90 degrees according to rule 1. Likewise, according to rule 1, we join points O and S together by a straight line. OS is the radius of the circle that is equal to 1, and according to rule 1, this angle cosine 90 degrees and this angle also cosine 90 degrees. By doing this construction, you can deduce quadrilateral OC OSCQ. This is quadrilateral OSCQ. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. That is to say, the sum of those four angles inside quadrilateral OSQC is equal to 180 degrees. Which angles we have inside quadrilateral OSCQ? We have 90 degrees plus 90 degrees, plus the missing angle SOQ, plus this angle that is theta. In total, must be equal to 460 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So if you follow that 90 degrees plus 90 degrees plus theta plus the missing angle SOQ, in total must be equal to 360 degrees according to the rule that I mentioned. 90 degrees plus 90 degrees is 180 degrees. So 180 degrees plus theta plus the missing angle QS, in total must be equal to 360 degrees according to the rule that I mentioned. Here we subtracted 180 degrees from this equation and found out that 360 degrees minus 180 degrees is 180 degrees, so 180 degrees equals to theta plus the missing S of Q. Here we subtracted theta from this equation and found out that the missing angle QOS is equal to 180 degrees minus theta in its side. This is the missing angle S of Q, this is equal to 180 degrees minus theta degrees in its size. But we already found out that 180 degrees minus theta equals to 139.632 degrees. So 180 degrees minus theta equals to 139.632 degrees in its size. We have the special formula that says that the area of any triangle that blocks a circle is equal to the semi-perimeter of the triangle times the radius of the circle that the triangle blocks. Again, the area of any triangle that blocks a circle is equal to the semi-perimeter of the triangle times the radius of the circle that triangle ABC blocks. We already found out that the area of triangle ABC equals to 2 times square root of 110. Again, we found out that the area of triangle ABC equals to 2 times square root of 10 square units in its size. So the area of triangle ABC equals to 2 times square root of 110 square units in its size. And we already found out that S equals to 11 times the radius of the circle the triangle ABC blocks. So the total we found out that 2 times square root of 110 equals to 11 times R. Here we divided this equation by 11, and finally found out that the radius of the circle that is described by triangle ABC is equal to 2 times square root of 110 over 11. 2 times square root of 110 over 11 is 1.9 or 0. So the radius of this circle that is described by triangle ABC is equal to 1.07 units in its length. In the next step, we join points O and C together by straight line. But before that, here we can implement all 2. If we focus on this connection point B, from this connection point B, we have 2 tangents to this circle, tangent BQ and tangent BP. And according to all 2, they are equal to each other. That is to say, BQ equals to BP. So if we define BQ as A, then BP must be also equal to A because they are equal to each other according to all 2. QC equals to BC minus BQ. So QC equals to BC, that is 9, minus BQ, that is 8. So in total, QC equals to 9 minus 8 in its length. So if we focus on this connection point C, from this connection point C, we have 2 tangents to this circle, tangent CQ and tangent CS. And according to all 2, they are equal to each other. That is to say, CS equals to CQ. But CQ is 9 minus 8, therefore CS must be also equal to 9 minus 8 in its length. Likewise, from this connection point A, we have 2 tangents to this circle, tangent AP and tangent AS, and according to all 2, they are equal to each other. That is to say, AP equals to AS. But AP, what is the length of AP? AP equals to AB, that is 6, minus PP, that is 8. So in total, AP equals to 6 minus 8. So AP equals to 6 minus 8, therefore AS must be also equal to 6 minus 8 units in its length according to all 2. What is the length of AC? AC is 7. But AC consists of 2 line segments, AS and SC. So AC is equal to 7, it is equal to AS plus SC. And AC equals to AS plus SC. So AC equals to AS, that is 6 minus 8, plus SC, that is 9 minus 8. So in total, AC equals to 6 minus 8 plus 9 minus 8. So AC in total equals to 6 plus 9 is 15, minus 8 minus 8 is minus 2, 8. So in total, 7 equals to 15 minus 2, 8. Here, we had that subtracted 7 from this equation, and we added 2a, simultaneously to this equation, and finally found out that 2a equals to a, and 2a equals to 8. Here we divided this equation by 2, and finally found out that a equals to 4 units in its length. This is a cubed equals to 8 equals to 4. PB equals to a equals to 4. AP equals to 6 minus 8. 6 minus 8, 6 minus 4, that is 2. Likewise, AS is 6 minus 8, that is 2. SC is 9 minus 8. 9 minus 8 is 9 minus 4, that is 5. Likewise, QC equals to 9 minus 8, that is 5. Our task is to find out the area of this green shape. So what is the area of the green shape? For the drawing, it is very easy to see that the area of this green shape equals to the area of quadrilateral OSCQ minus the area of this circle SOC. Again, the area of this green shape equals to the area of quadrilateral SCQ OSCQ, this polynomial, minus the area of this sector, QOS. Okay, again, the area of the green shape in total equals to the area of polynomial OSCQ minus the area of sector OSQ. It is very easy to see from the drawing that polynomial QOSC, this polynomial consists of those two right triangles. And therefore, the area of polynomial OSCQ must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is this right triangle OSC, plus the area of the second shape, that is this right triangle OQC. Again, the area of the polynomial OSCQ must be equal to the sum of the areas of the two shapes that it consists of. The first shape is right triangle OSC plus the second shape, so it is the area of the first shape, that is triangle OSC plus the area of the second shape, that is the right triangle QOC. And therefore, the area of polynomial OSCQ must be equal to the area of triangle OSC plus the area of triangle QOQC. So from the area of polynomial OSCQ, we have to subtract the area of this sector QOS. Actually, we know that the area of any sector equals to the area of the sector that contains the sector, pi r squared, times the angle between the legs of the circle, 139.632 degrees over 360 degrees. And therefore, the area of sector OSQ must be equal to pi r squared, that is the area of the sector that contains the sector, times the angle between the legs of the sector, that is 139.632 degrees over 360 degrees. The area of triangle OSC equals to the base OS times the height SC over 2. Again, the area of triangle OSC equals to the base OS times the height SC over 2. Plus the area of this right lower triangle QOS. The area of this right lower triangle QOS equals to the base OQ times the height QC over 2. Again, the area of lower triangle QOC equals to the base OQ times the height QC over 2. Minus the area of sector OSC is equals to pi r squared times 139.632 degrees over 360 degrees. R is 1.907, and therefore r squared equals to 9.907 squared. So pi r squared is pi times 1.907 squared times the angle between the legs of the circle of the 139.632 over 360 degrees. OS is the radius of the circle, that is equal to R. SC is 5. And OS is the radius of the circle equal to R. SC is 5. And we have to divide it by 2. Likewise, OQ is the radius of the circle equal to R. SC is 5. And OQ is the radius of the circle equal to R. QC is 5. Divided by 2. Minus the area of sector OSQ. In total, the value of this expression in total equals to 4.387 square meters in size. So the area of sector OSQ equals to 4.387 square meters in size. 5r squared plus 5r squared is 5r. So the area of the green shape in total equals to 5r minus the area of sector OSQ, that is 4.387 degrees square meters in size. 5r minus 3.87 degrees equals to actually 5r is 5 times 1.07, this is the radius of the circle. 5 times 1.907 is equal to 9.535 units. So 9.535 minus 4.367 is equal to 5.14 square meters in size. So in total, we found out that the area of the green shape equals to 5.14 square meters in size. The area of this green shape, it is equal to 5.148 square meters in size. Thank you very much.